So we're running a tutorial on how to run a correlation using the worksheet from class. In this case we want to see whether there's any relationship between the amount of push-ups that someone can do and the amount of time that they can hold an isometric hand squeeze. So we have our two sets of data here. What we're looking for in this is 4 sets of values. The first is the R value, or the strength of the correlation, and this also indicates the direction, whether it be positive or negative. The R squared, the coefficient of determination, this is interpreted as the meaningfulness. In other words, how much of one can explain the other, the percentage variance of one variable that can be explained by the other. The P indicates the probability, that is, the probability of this effect being due to chance. Remember that we are always comparing this to alpha, that is, to see whether it is less than 0.05, and therefore if the P value was less than 0.05, we would say that there is less than a 5% chance of this relationship being due to chance or being due to some unlikely scenario. Finally, we want the 95% confidence interval of the R value, not of the raw values themselves, but of the R, of the correlation. If I can explain this using a schematic here, imagine that we have our correlation value of 0.81, and when we get the confidence interval, this tells us the range of possible scores that R could be in a population. If we see in this case that actually R varies quite considerably, that means of course that we have less confidence in this correlation. As with anything, if we increase the sample size, this increases our confidence or the accuracy of the statistic that we are undertaking. In this case, our R value could actually range from 0.44 all the way up to 0.93, so this is quite a large variance in the true R value that we are interested in. Consider a second scenario then, where we have the same R value, in other words the mean or the correlation is the same, 0.81. However, this time our confidence interval range is much smaller. We have more confidence in the true value of R being close to 0.81. This only ranges from 0.78 up to 0.84. Therefore, the closer we are to the true value, or the more confident we are in our set of data, the smaller the confidence interval will be. For our assumptions for a correlation, we have to consider that the data is collected randomly, and we'll assume that it is, that we have high level data. Remember, we can have high level as scale or continuous data, and we can see that this is the case here. So push-up amount, this is continuous scale, as well as the amount of time that someone can hold an isometric hand squeeze, this is measured continuously over time, time being a continuous scale. So we have high level data. The third thing that we're interested in is to check whether there are any outliers, because of course this will influence the normality or the shape of our bell curve, and then we can check for normal distribution itself to see whether we have a normal distribution in both our sets of data. Finally, we also have to assume that we have a linear relationship between these two sets of data. If it's not linear, then we cannot run a Pearson product moment correlation, which gives us this R value. So we can do the final one here first by selecting both our sets of data, go to Insert, Scatter, and insert the scatter like this. In this case, we can see that there is definitely a linear relationship between our data. There is somewhat of a straight line, with one maybe potential slight outlier here, but I don't think it's big enough for us to be concerned with. If I click on the plus sign here, I can actually add a trend line, and this will of course show me that this is indeed a linear relationship, as you can see here. Now, as most of you are aware, we can double click this line and select the option to display R squared on the chart. But this is skipping slightly ahead of ourselves. We should really attempt to achieve this value in SPSS. So let's copy our data, Control and C, and take it into SPSS. I'm going to open up the SPSS, and the first thing that comes up is this window here. We type in the data and click OK, and this blank window will come up. Let's go to our first cell here and Control V, or paste in the data. Again, making sure that we've only copied in the numerical data, the numbers of the two variables. If we copy in the names as well, then we have an issue here in that in variable view, the second tab at the bottom here, the type of data will change from numeric to string. String basically means that it's looking for letters instead of numbers. So we have to make sure that this is always numeric if we're going to run statistical tests on this data. We can then name our data in the first column here in the variable view. Let's call this push-up. Remember, we can't put spaces in this section. And let's call this one isometric. The final thing we should do in this variable view tab is to specify the data level. As we've just discussed, this is high level, continuous or scale data. So in here we have to make sure that we select scale as a measure in this case. So if we go back to the data view, we can see now we've renamed our data to push up and isometric, and it's well prepared here for us to check our assumptions. We've already checked that we have a linear relationship. So we're going to go to Analyze, Descriptive Statistics, and to Explore in order to check both outliers and a normal distribution at the same time. These are of course dependent variables, so we have to copy them into the dependent list by clicking this button, or else you can drag them across into the list like this. We have our two into our dependent list. These are the ones that we're going to run our tests on. Let's click on Statistics and make sure that we select Outliers in the option here. Let's also click on Plots and make sure that we click Normality Plots with Tests to check the normal distribution using the Shapiro-Wilk test. And continue and click OK. A second pop-up window will arise, and from this again, don't be too concerned with the fact that there is huge amounts of data that come out of this test or this system. We just want to look for the ones of which we are interested in. And of course the first thing that we want to do is look for outliers in the data, and we do this by looking at our box and whisker plots. So if we scroll down to the output, we will keep going until we find the first box and whisker plot, in this case here, and underneath we can see that the word push-up is there. So this is indicating the box and whisker plot for the push-up variable. We can see, of course, because there's no dots above or below our box and whisker plot, that we have no outliers present in this data. Let's continue down into the isometric data. We see here's our isometric, and again no outliers indicated on the box and whisker plot. So we're good for outliers, we don't have to delete any in this case. Let's go back up and now look for our third and final assumption, which is our test of normality. In this output box here, test of normality. Here we're interested in the Shapiro-Wilk output, looking at the significance values here, and to pass this assumption they have to be non-significant. In other words, these values have to be greater than 0.05. So why is that? Well, the test of normality using the Shapiro-Wilk option will test our variables against a perfect distribution, doing a simple difference test. In other words, it's asking the question, is our variable, for example push-up, significantly different in distribution than a perfectly normal distribution? And of course it is only different if we have a significant p-value, or less than 0.05. Because we do not want it to be different, this value then should be above 0.05. And we can see in this case that both of them are indeed above 0.05, and therefore we have a normal distribution in our data. Let's proceed then to run our correlation test. From here we can go back to this option of Analyze, down to Correlate, and click on the bivariate option. Remember, bivariate meaning bi for two and variate for variable. Two variables that we are correlating together, which is what we're trying to do in this case. When we select the option, again we have the option of choosing whichever variables that we want to correlate and dragging them into the variables box. Again, if these are not indicated as scale data, as you can see by the ruler here, then you will not be able to copy these across. So there's something wrong with the way you have set up your data. There are no options that we need for this, we just have to make sure that the appropriate correlation is ticked. In this case, the Pearson product moment correlation, which is ticked here. Let's click OK. We see here in the correlations output that we have push-up and isometric here with a Pearson correlation. This is called a correlation matrix. If we're just interested in the interaction or the correlation between the two, we come across from the push-up row until it intersects with the isometric row here. This is quite easy to do with just two variables. When we have a bigger correlation matrix, it's a little bit more tricky. So push-up, the correlation value, the first row here across in its correlation with isometric. The R then is 0.867, or an R of 0.87, which would we consider a moderate to strong correlation. The significance, or the p-value, then is read here as 0.000. However, we are aware that we can never have absolutely no probability of something being due to chance. There is always a slight chance that the value could be wrong. Therefore, we would report this as p is less than or equal to 0.001. These are the two values that we'll take from here, and we'll copy them into our Excel file here. So we're looking for, remember, the R value. In this case, our R was equal to 0.87, just rounding up to 2 decimal places. Our P value, if we go to insert a symbol, this insert symbol, we can use this less than or equal to sign, insert and close, less than or equal to 0.01. That was our P value. So of course we compare this to our alpha that we specified at the start, and of course we can see here that 0.01 is less than 0.05, so we have a significant correlation. That is, that the probability of this correlation being due to chance is less than 1%. So that means we're very confident in the probability of this data being true. We have our strength of the correlation then. Again, it's positive, it's not a negative value, and we can see that in our graph here. We have a positive correlation of 0.87. Now I've revised how to interpret how strong the relationship is here, just to make it a bit clearer for you. So if we go back to our correlation lecture notes, we see that Evans 96 interpreted absolute correlations as follows. 0 to 0.2 is very weak, 0.2 to 0.4 is weak, 0.4 to 0.6 is moderate, 0.6 to 0.8 is strong, and 0.8 to 0.1 is very strong. So in fact we would interpret this correlation that we have of 0.87 as a very strong correlation. So we still need to calculate the R squared, and we have to calculate the 95% confidence interval of this data. So the R squared is quite simple, because we just simply take our R value and multiply it. So I put equals and selected the 0.87, put in a multiply sign and multiply it by itself by the same 0.87. Now we arrive at a value of 0.76. By using this option here, I can just bring down my decimal place, 0.76, or 76%. That is, that 76% of one variable can be explained by the other, which is an exceptionally large value for this R squared, and therefore we should be very confident that we have a strong correlation or relationship between these two sets of data. The final thing that we need to calculate is the range of possible scores of which R could be. For this we have to go to our effect size calculator. When we open this, make sure we selected the tab Correlation Confidence Interval, and it's very simple to use. We just take our correlation, 0.87, and put that into the yellow box here, and we make sure that we have the correct sample size. So we go back to our other data. Let's just check that how many we have here. Let's highlight them. And the bottom here it says we have 16. So we do have a sample size of 16. So a correlation of 0.87. Let's just check that that's right. Yep, 0.87. A sample size of 16. We see here our 95% confidence interval is 0.6 to 0.9. So we'll copy and paste, or else just type that data into our results here. There is our upper and lower limit for our two values. I'm going to just push the decimal place back here to make it a bit easier to read. So we got a value ranging anywhere from 0.66 up to 0.95. This is the lower limit, and this is the upper limit for our confidence interval. So they are all the steps involved in calculating the values that we need to interpret a correlation. However, as I'm sure you're aware, it's the interpretation of this correlation, or the statistic that we've just ran, which is important. So in this case, we would claim or state that when examining the correlation or the relationship between push-up ability and isometric hand squeeze, we found a strong positive correlation that was significant, and where the range of possible scores range from 0.66 to 0.95 for the correlation. In addition, we can say that 76% of one variable, or the variance in one variable, could explain the other, which is a very high coefficient of determination or meaningfulness measure.